Alright, in this video we're going to be talking on inductive effects, electromeric effects, and the differences between inductive effects and electromeric effects. Okay, let's start with inductive effects. This is an effect whereby non-polar bonds become polar due to polarity by adjacent bonds. I don't know if you got this definition. Non-polar bonds that are normally non-polar, they end up becoming polar due to polarity by adjacent bond. This is a permanent effect and it's due to electronegativity difference in bond species. It occurs in sigma bonds only. All these points are very important. It leads to the formation of dipoles. There are two types of inductive effect. There's the positive inductive effect. Positive inductive effect are the inductive effect, if I put it that way, caused by positive charges, therefore making the non-polar bond or the bond that was non-polar before take a negative charge due to the electronegativity difference. It will end up donating electrons, like keep donating electrons to that one and make it electron rich, right? Making the making the other bond electron deficient. That's just how the first one is. The second one is negative inductive effect. That means electron withdrawing bonds. I'm actually going to talk about this later on, so let's go on. Now, like I said, positive inductive effects. This is electron donating or electron releasing inductive effects. It is found in bonds that donate or release electrons. Example of those bonds are methane. Just note something: most alkyl groups, they are electron donating. They like to donate electrons to the other bond pair, and that is what is happening here. That's why you see the first example is methyl, the second is ethyl, the third is propyl. Then also carbon dioxide can also do this. Now, these groups donate electrons or release electrons to the carbon atom, thereby making it electron rich. If I may give you an example, let's say this is a carbon atom. Let's say this is a carbon atom and it's bonded with an alkyl group, let's say methyl. Now, actually, what methyl is going to be doing is that methyl is going to be donating electrons to this, therefore making methyl electron deficient. I'm making this carbon electron rich. Now, this will actually lead to the formation of a dipole. Dipole, or what should I say, partial charges, if I put it that way. That means they will actually, this carbon here will actually be partially negative and this will actually be partially positive. I don't know if you understand that mechanism. They are not actually ions yet, they are still bonds. But this is so rich in electron that it's actually taking a partial negative charge, right? This is so deficient, it's actually taking a partial positive charge. This effect is a permanent effect, like I said before. It doesn't change like with time, or what should I say. It's a permanent effect. This always keep donating its electron. This always become electron rich. It never breaks, like the bond is always permanent. Now, I don't know. Okay, negative inductive effect. This is an electron withdrawing effect. That means the bond pair, they always like withdrawing electron. This is mostly found in groups with high electronegativity. Such groups include chlorine, bromine, so on. You can see fluorine, cyanide, so on, thiocyanide, or thiosulfate, different groups, nitro groups, and all these other groups. These groups are electron withdrawing. That means they like absorbing, or what should I say, taking electrons to themselves. They take the electron from the carbon atom, thereby making the carbon atom electron deficient and making themselves electron rich. Now, let me also give an example on that. Now, I have something like, let's say, a chlorine atom is attached to a carbon atom. Now this chlorine, because of its high electronegativity, what it's actually going to be doing is that it's actually going to be withdrawing the electrons of this carbon. It's going to be withdrawing the electrons of this carbon, thereby acquiring a partial negative charge. Sorry. It's going to acquire a partial negative charge, something like this, and the carbon is going to acquire a partial positive charge. That's actually what is just happening here. They're actually going to acquire different partial charges, and therefore what is actually going to be doing is actually going to be inducing on this carbon, and depending on the number of carbons, actually, let's say this carbon keeps bond like with another carbon, another carbon, another carbon. Now the induced effect on this carbon number one, will be greater than the induced effect on carbon number two, greater than that on carbon number three. So I can see the induced effect. Let me just see. That is, what shall I say? The induced effect of carbon number one is greater than that of carbon number two, greater than that of carbon number three. And that is actually all about induction effect. Just know that from the name induction effect, it's actually inducing on one, affecting the other. Just use your normal English and we can be able to decode it. Now, electromeric effect. This effect is the complete transfer of electron shared by two parties to one of the members in the presence of an attacking reagent. Now just note this: unlike induction effects that they acquire partial charges but they are still bonded together, they are still joined by a bond, electromeric effect is the complete transfer. That means the bond will actually break, it will actually split because of the presence of an attacking reagent. No, this is very important. This is very important. It's the attacking reagent that actually causes the bond to actually break and therefore leading to the formation of ions, if I put it that way. This is a temporal effect as electrons return to their original position when the attacking reagent is removed. So it's a temporary effect. When the attacking reagent is removed, the electrons actually return back to the original position. The bond is formed again. It occurs through the pi bond because the pi bonds are mobile bonds. Now, if we can notice something from induction effect occurs in the sigma bond. Why electromeric effect occurs in the pi bond? Why? Because the pi bond, we all know the pi bonds are mobile bonds. They are free to move about. Like mostly in all this conduction and whatever, it's mostly actually the pi bonds. The sigma bonds can't move about. It's the pi bonds. They are mostly like the free electrons and they are the mobile bonds. This means it can never be seen in single bonds, because we all know single bonds, like single bonds C to C, they are not the bond there, it's a sigma bond and it's not a pi bond, so I can actually represent this by a sigma sign. But in a double bond, something like, let me just take this, in a double bond, something like this, C, this first bond actually is going to be a sigma bond, this second bond is actually going to be a pi bond, and this pi bond here is actually going to be the mobile bond. This is the mobile bond. That's why I say it can only be seen in multiple bond. This is not mobile, immobile bond. So another example, triple bond C. This remains the sigma bond, while these two bonds actually become pi bonds. So that's actually what is happening in all of this. So now note something: electromeric effects aids and never inhibits a reaction. Now we can take this back to our physical chemistry and we can actually decode this. For a reaction to occur, the ions needs to be formed. That means there are different energies that need. We all know for a reaction to occur, ionization energy, the energy supplied must be greater than the ionization energy. Ionization energy is the energy required to actually break a bonds and form ions. for this to occur, there are also different energies that needs to lattice energy and so on. Now, electromeric effect aids because it's just like leading to the formation of ions without the like it aids the formation of ions. The ionization energy that needs to be acquired is just like a catalyst actually decreasing the ionization energy because the ions are formed at a lower temperature, at a lower energy level, and so on. So that's why I say electromeric effects aids and never inhibits a reaction. Now, I'm just actually going to give you an example of electromeric effects. So let's just say Rx. This Rx, we all know R is the symbol for alkyl and X for halogen. In the presence of an attacking reagent, it could be any reagent like their specific reagents. This is the attacking reagent. What happens is that this RS it actually breaks, and the way it breaks is that it splits heterolytically. That means this bond here, this bonding pair bond, will actually move to the halide ion and will then end up forming an alkyl group, like an alkyl group, a positively charged alkyl group, and a negatively charged halide ion, and these are ions. And this alkyl group, it can be a carbocation, it can also be an icarbanion. Let's give an example, something like R with CH3, and this splits in presence of an attacking reagent. We can also have something like R minus and CH3. Now we all know that when it's R minus, okay, let me clear the board. When it's R minus, we have a carbanion. When it's R plus, we have a carbocation. Or carbonium ion. And so we all know of this, so let's keep going. Now, the last one I'm actually going to be talking about is the difference between inductive and electromeric effects. Now, if we look at what I've been saying earlier, we find out that these two effects, they can be compared together. So we can actually like bring comparisons between both effects and differentiation between both effects. You can actually get the comparison, or I can actually like take some out later, but let's just see the difference now. Now, inductive effect, like I said earlier, it occurs in the sigma bond only, while electromeric effect it occurs in the pi bond. It never occurs in the sigma bond. That's like one of the major differentiations between them. The second thing, inductive effect can be found in single or multiple bonds. Like I said, single bonds, multiple bonds, they also have sigma bonds. Every multiple bond, I gave you something earlier. It's like a double bond will have one sigma bond, triple bond, one sigma bond, both of them. So it can occur in both single and multiple bond because of the presence of sigma bond in both single and multiple bond. While electromeric effects can only occur in multiple bonds. Now, inductive effect is a permanent effect. It will always keep inducing one of the, like taking electron is a permanent effect, while electromeric effect is a temporary effect because immediately the attacking reagent is removed, it's over. Inductive effect is due to electronegativity difference between the two bonds. Because of the difference in electronegativity, one will always like be electron withdrawing while the other one will be electron donating. Why electromeric effect is due to the presence of an attacking reagent. When the attacking reagent is removed, electromeric effect stops. Inductive effect is leads to like it is due to partial transfer of positive and negative charges. Electromeric effect is due to complete transfer of positive and negative charges. Inductive effect, it will lead to the formation of a partial positive charge and a partial negative charge. Electromeric effect leads to the formation of ions. Ions have full positive and negative charges, while what should I say? Partial charges, they have partial positive and negative charges. Now, inductive effect leads to the formation of dipole moment. We all know dipole moment is due to partial charges, while electromeric effect doesn't form dipole moment. Bond pair is always polar. Polar effect, like we all know, bond pair is always polar. That's something we need to take into consideration. Due to electronegativity difference and everything, it can actually interact with water, and that's what polarity mostly depends on, because water is also like seems water also have like partial positive, partial negative charge, and due to the dipole moment formed, what actually happens is that the bond actually like splits in water, and the water bond actually also splits, and then it floats it in. Once you're doing solutions, you actually get this better. Now, bond pair might not be polar. Like I gave you an example earlier. In that example, I showed you a carbon atom with a methyl group. That bond can be polar. It's non-polar, but yet it can still undergo electromeric effect. Now, there's no formation of carbocation, carbonium ion, and carbanion, like I told you earlier. In inductive effect, there's only formation of partial positive and partial negative charge. That is not carbocation is a positively charged carbon atom. Carbanion is a negatively charged carbon atom. While in electromeric effect, there is the formation of carbocation or carbonium ion and carbanion. Sorry, that was meant to be carbanion. So that is all the point we need to know. Now, like I said I'm also going to give you like comparisons, but you can actually decode it from both of them. Like, what you can actually decode is that electron transfer, there can be like electron, it's actually going to be transferred. One must actually be electron rich and the other must be electron deficient. That means there must be, let me just check if I see our space. Okay, the comparison, if I put this here, so let's just go. Like, electron transfer must always occur. Must always occur. It can be found, like, if I, okay, that won't be good. Let's also think of another one. Okay, just take this. This is like the most important stuff. Most of the time they don't ask you to compare both of them, but if they ask you from your knowledge of this that I've actually thought of, you can actually decode it. It's because I didn't actually prepare a slide on this, so if I want to decode it, I'm actually going to spend a lot of time, but I'm sure you're able to do it. But just get this first one. Okay, thank you for watching this video. Please like and subscribe to my channel. Thank you.